u cos 2 pi by n. Yes, relative velocity of this with respect to this will be resolve this u cos 2 pi by n in this direction. Yes, so this will be u minus u cos 2 pi by n. So this will be relative displacement and this will be relative velocity. Now this is the time after which the two particles will be meeting. If he is giving you a square, put n equal to 4. If he is giving you a triangle, put n is equal to 3. Pentagon, n equal to 5. You will get the time after which they meet. Why should relative displacement be A? Relative displacement will be initial separation minus final separation. You know all these particles will meet at the centroid. So if I try to keep this particle at rest, it will feel that this particle moved straight towards this. Yes. Only then the two particles will meet. Straight towards means it will feel that this particle had a displacement of A. And that A is what you are giving here. Relative displacement by relative velocity. Now listen to this carefully. This is the toughest problem in whole of this subject of relative velocity in kinematics. Mainly because it involves calculus. You are dealing with the same concept. But in this concept of equilateral triangle and this, you had the advantage that you knew where the particles will be meeting at the centroid. So you knew that they will be meeting, first case. Second case, you knew where they are meeting. Hence you said relative displacement by relative velocity, your job was done. But what if it is not a symmetric case? You will have to use calculus because things are varying. You will have to consider a very short time interval, find out the relative velocity in that time interval and then integrate all throughout. In this particular case, have a look at this. There is one particle here and one particle here. Particle 1, particle 2. Now this, both of them, initial separation is L. Initial separation is L. Now both started moving simultaneously. Both started moving simultaneously. First particle was moving with a velocity of v. Second particle was moving with a velocity of u. But the second particle is always aimed at the first particle. But the second particle is always aimed at the first particle. See, first particle is moving straight, linearly, with uniform velocity. Second particle has a constant speed. Mind my language, I am using the word speed. Sorry. Yes, sir. Second particle is moving with a constant speed u, but always aimed at particle 1. But always aimed at particle 1. So as this particle came here, this will change its track. So gradually it will meet this trajectory somewhere here. Convinced? Because always the particle 2 is aimed at particle 1. Say when particle 2 is here, when I draw u here, the particle 1 will be here, moving with the velocity of v. This is the question given. Now here we don't know where they will meet. What are the conditions that they meet? I just cannot tell you relative displacement by relative velocity. As a result of which, I will have to consider a very short time interval. Why are you considering a very short time interval? In that short time interval, the direction of the particle 2 will remain constant. Yes, sir. In that very short time interval, the direction of particle 2 will remain constant. So in that short time interval, if I consider this angle to be alpha, this angle will be alpha and the velocity of this will be v cos alpha. Do you agree with that? Yes, sir. Now the relative velocity between the two is u minus v cos alpha. Do you agree with that? Yes, sir. Velocity into time dt. Do I get the relative displacement dl? Now this is relative velocity into time dt. This will be the relative displacement. Now why did you take it this way? You have taken a short time interval because in that short time interval the velocity of u will remain constant. In this short time interval the relative velocity of u will remain constant. So relative velocity of approach will be u minus v cos alpha. That into time will be the relative displacement, which I shall integrate. But obviously I will put a negative sign before this because the relative displacement is decreasing. What is relative displacement? You are trying to describe the motion of one with respect to the other. If I consider myself to be at rest, that particle, I am going straight this way, that particle is following me. So the distance between us is decreasing. So I will consider myself to be at rest and that particle is approaching me. So the distance between us is decreasing. Hence, if something is decreasing in calculus, we have learnt dy by dx will be negative.
Yes, sir.
And here it was dl by dt, which I wrote this way. My original equation was dl by dt. This is relative displacement in a time interval dt was u minus v cos alpha. So obviously I will be preceding this with a negative sign. Because this parameter L is decreasing. Initial separation between them I am taking as L0. Final separation will be 0. Finally the two particles are meeting. When the separation between them is L0, time is 0. When the two are meeting, the time is capital T. This is the heart and soul of this particular problem. Did you understand this equation?
Yes, sir.
All of you?
Yes, sir.
Excellent. Now see the typical structure of solving this. U integral dt 0 to t minus v cos alpha dt 0 to t is equal to L with a negative sign L0 to 0. This will be ut minus v integral cos alpha dt 0 to t is equal to L0. Right? Is equal to L0.
Yes, sir. Yes, sir.
To simplify this, I am stuck up here. I know integral cos theta with respect to theta. I know integral cos theta with respect to theta. Integral cos alpha with respect to alpha. Integral something with respect to the same variable. But integral cos alpha with respect to t is not known to me. So what best can we do? Either we should use a mathematical tool or we go ahead with one more way, the alternate way. What is that alternate way? Look at the alternate system. By the time this particle travelled a horizontal distance of this, particle 2 also had the same horizontal displacement. By the time particle 1 travelled this horizontal distance, particle 2 also travelled the same horizontal distance.
Yes, sir.
By the time 1 travelled this particular distance, this is v into t. By the time 1 travelled this distance v into t, particle 2 also had the same horizontal displacement. Now how do I get that horizontal displacement? Watch out for this here. In this short time interval, can I consider this to be this short time interval? Look out for the velocity u cos alpha into dt. This is u. To calculate the horizontal displacement of this particle, I have a small trouble. U's direction is changing continuously. So I will get the horizontal velocity as u cos alpha. That u cos alpha will be the velocity only in that short time interval. Few seconds from then the angle alpha will change. So in that very short time interval, the horizontal displacement will be u cos alpha. Is everybody convinced?
Yes, sir.
So u cos alpha into dt is this short is the horizontal displacement in this short time interval. In the total time interval of 0 to t, can I call that to be the total horizontal displacement of the particle 2? In the total time interval, see in the short time interval of dt, u cos alpha will be the horizontal velocity of the particle. That into dt will be this horizontal displacement.
Yes,
In
sir.
the total time interval of 0 to t, if I integrate, can I call this to be the total horizontal displacement of the particle 2? Say something.
Yes, sir.
If you are not convinced, I'll redraw this diagram again. Have a look. See, I took a short time interval. This is u. This is alpha. This is u cos alpha.
Yes, sir.
So u cos alpha into dt, I will get this short time interval u cos alpha into dt. That will be the horizontal displacement in that short time interval. Add up all those horizontal displacements. Add up all those horizontal displacements. It will be from 0 to t.
Yes, sir.
Right? The total horizontal displacement will be from 0 to t. Now if this is the total horizontal displacement u cos alpha into dt from 0 to t, the horizontal displacement of particle 2 and the horizontal displacement of particle 1, don't you think should be the same? Only then they will meet. Now particle 1 is going straight, so the horizontal displacement is v into t. Now indirectly you got the value of this integral cos alpha dt. Now u is u integral cos alpha dt, 0 to t is vt. V by u into t is integral cos alpha dt, 0 to t. Substitute that here. Ut minus v into cos alpha dt will be vt by u is equal to L naught. So u square minus v square by u into t is L naught. If you want the time after which they meet, implies time after this way they meet is u L naught by u square minus v square. U L naught by, am I right? Yes, u L naught by u square minus v square. If you observe carefully, you will understand one parameter. What will be the condition that the two particles will meet? Means the condition would be the time should be positive. Now when will the time be positive? If the value of u square is greater than v square. That means the magnitude of u should be greater than v. That means the speed of this should be greater than the speed of this.
Yes, sir.
If you people watch these discovery channels or animal shows, sometimes they'll show you a tiger or a lion chasing its prey from the top view.
Yes, sir.
If you observe, the deer will be running this way and the tiger will be taking a turn in this direction. It takes a turn. Did you observe this?
Yes, sir. Yes, sir.
Now there the speed of the tiger should be greater than the speed of that particular prey. Only then it will be able to catch the prey. Here u should be greater than v. U is the velocity of this. Only then it will be able to reach this particular point. To make the problem a systematic problem, they said particle 1 is going in a straight line. In actual practice, particle 1 will be running in this direction and 2 will go and catch up this way somewhere here.
Yes, sir.
Right? In all principles where 1 is changing its direction, when 1 is changing its direction, this will be the procedure that you will follow here. I'll dictate the problem. While taking it down, understand every bit of it and every inch of it. You have a doubt at any point, tell me. I'll clear that and then you will go ahead with it. First of all, write down the problem. Particle 1 moves with uniform velocity v, while particle 2 starts simultaneously and is always aimed at particle 1 as shown in the figure. Find the time after which they meet. Take down the solution. Understand every step of the solution while taking it down. You have a trouble with it, kindly let me know. Original source of the problem is from Irido. The problem is as it is picked up from Irido. Yeah.
I did not get the step. You took the first step, integral u minus v cos alpha.
Right.
Yes.
Now here I'll actually have to put relative displacement by relative time is relative velocity. Right?
Yes, sir. Yes.
Now relative displacement is dl. In that time interval dt, this will be relative velocity. Now relative velocity, here you took a small time interval. Why are you taking a small time interval? Relative velocity into small time interval is relative displacement because the direction of u is continuously changing. So you considered a very short time interval. In that short time interval, the velocity of u is in this direction. In that short time interval, you can assume the direction of u to be constant.
Yes, sir.
And if you assume direction of u to be constant here, this is angle alpha. This is angle alpha. So here, if this is alpha, this being alpha, I'll resolve v in this direction. Relative velocity in that short time interval is u minus v cos alpha. Relative velocity of 2 with respect to 1 will be u minus v cos alpha. This will be the relative velocity into time will be relative displacement. That I integrated from 0 to t. Here I am integrating with respect to time. Here I am integrating with respect to relative displacement. Initial separation is L naught. Final separation is 0. And because this is decreasing, I preceded this with a negative sign. My trouble came when I had to integrate this. Integral cos alpha dt. Now I do not know the integration of this. I know integral cos theta d theta. Integral cos x dx. Cos alpha d alpha is known to me, not dt. I should get this as a function of t or search for an alternate means. What is that alternate means? The horizontal displacement of this should be equal to the horizontal displacement of this. Only then the two particles will meet here. Now the horizontal displacement of this is v into t. The horizontal displacement of this is v into t. The horizontal displacement of this, in that short time interval, I put it as u cos alpha into dt. In that short time interval, that I integrate from 0 to t, I will get the total horizontal displacement of this. Right? Equate both. You will find one condition, integral cos alpha dt. Substitute that here, you get the answer.
In this case, we have taken the direction of the relative velocity in the direction of u of particle 2.
Yes.
So, if we take with in the direction of v or particle 1, so how will we have to construct the
We have a
relative
small
velocity?
discomfort there because 2 is always aimed at 1. So I took relative velocity of 2 with respect to 1. So I will have to take this velocity minus this velocity.
Yes, sir.
Right? So I went ahead in that particular direction. If you do the reverse, obviously we will understand that 1 will appear to come towards 2. Right? But then why did you take it this way? Means in the question 2 is approaching 1. So relative velocity of 2 with respect to 1 is taken. Hence you took it along the direction of those two relative velocities. Now in the same problem, watch out for this. What if magnitude of u was equal to magnitude of v? In the final answer that you got, denominator you had u square minus v square. If both the speeds are the same, what is the time after which the two particles will meet? They will never meet, rather I would say mathematically infinite amount of time.
Right.
Okay, now obviously even if it is equal, they will not meet. If by chance u is greater than v, they will meet. If v is greater than u and 100%, they will not meet.
Yes, sir.
Now watch out for this. The question is like this. The same question. This is particle 1, particle 2. Temporarily for you to understand what I am taking this as v and this as u. But the question is u is equal to v. So if u is equal to, they will not meet. If u is equal to v, they will not meet. But then what will happen? U is always, the second particle is always aimed at the first particle. So if the second particle is always aimed at the first particle, now this will be the position of the second particle and this will be the position of the first particle after some time t. I am taking this as L naught and the distance between them will be d. In the sense, 2 is always aimed at 1. Once it gets on to this cycle, 2 will always be aimed at 1 and both of them are going with the same speed. So thereafter the distance between them will remain constant. Thereafter the distance between them will remain constant. So he is asking you for the relation between L0 and D. He is asking you the relation between L0 and D. How do we go about with this? Consider this to be u. I am temporarily taking this as u and I am taking this as v so that you understand which is taken with respect to what. In the last step, I will substitute u is equal to v. So in a small time interval, this is alpha and this is alpha. This is v cos alpha. This is alpha and this is alpha. This is v cos alpha. U minus v cos alpha into dt will be relative velocity into time. This will be equal to the relative displacement.
Yes, sir.
The only difference is with a negative sign. The initial separation is L0, the final separation is D. In the previous case, I put this as 0. Please concentrate on this. This is the toughest slot in kinematics. Understanding this is very difficult. If you don't concentrate, you will not get this. Now, this is L0 and this is D. The initial separation and final separation. L0 is the separation when the time is 0. T is the separation. T is the time.